Hello friends, welcome to YouTube channel Electronics. Today we will learn about series and parallel combination of capacitors. When capacitors are connected in series means connected one after the other in a single line, then the total capacitance equal to the sum of the reciprocal of the individual capacitances. When capacitors are connected in parallel means both of their terminals are respectively connected to each terminal of another capacitor, then the total capacitance is equal to the sum of the individual capacitances. The equations for series and parallel combination of resistors and capacitors are just opposite to each other. By connecting capacitors in series is equivalent to increasing the thickness of the capacitor. So the distance between the plates and thickness of the dielectric material will increases. The value of capacitance is inversely proportional to the distance between its plates. The electromagnetic field or attraction between positive and negative charges becomes weaker. Hence the capacitance reduces in series combination. The amount of charge stored in a capacitor calculated by using the formula charge equals to capacitance in farads multiplied with voltage. So the charge stored in this 10 volt 100 microfarad capacitor is 0.001 coulombs. We can calculate energy stored in a capacitor using the formula 1 by 2 multiplied with capacitance in farads multiplied with voltage square. So this 100 microfarads and 10 volts capacitor can store 0.005 joules of energy. For series connected capacitors, the charging current flowing through the capacitors is same irrespective of their capacitance values, because current has only one path. Just imagine that we have three empty tanks of different sizes and we have connected them through pipes at bottom. If we fill water in them, all the three tanks will have equal level of water irrespective of their sizes. Likewise, in series combination, the amount of current flowing through the circuit is same. If it is 2 amperes when measured at the input, it will be 2 amperes current at any point irrespective of capacitance values. So we can say that current through the network I1, I2 and I3 are equal. Suppose three capacitors of different values are connected in series. If we apply a voltage across this circuit, the capacitor C2 is effectively isolated from the circuit because of the dielectric or insulating material in C1 and C3 capacitors. Here the positive potential of the supply attracts the electrons from capacitor C1's plate, making it more positive, while the negative terminal of the supply forces the electrons to the C3's plate, making it more negative. As we know, same polarity charges repulse each other, while opposite polarity charges attract each other. So here the negative charged electrons in capacitor C3 repulse the electrons in its other plate. These repelled electrons will get collected in capacitor C2's plate, which is directly connected to it. So here two things have happened. Capacitor C3 is charged with positive and negative charges, and one plate of capacitor C2 is negatively charged. These negatively charged electrons on capacitor C2's plate repulse the electrons in its other plate. So the capacitor C1 and C2 will also get charged up. Therefore, each capacitor will store same amount of electrical charge on its plates irrespective of their capacitances. This is because the charge stored by a plate of any one capacitor must have come from the plate of its adjacent capacitor. So the capacitors connected in series have same charge. Total charge Qt and individual charges Q1, Q2 and Q3 are equal. This will result the effective capacitance has decreased to the smallest individual capacitance connected in the series network. As the capacitance is inversely proportional to voltage, the voltage drop across each capacitor will be different depending upon the values of the individual capacitances. The smallest capacitor will have the highest voltage drop across it. When capacitors are connected in series, the current flowing through the network is same. The magnitude of charge Q on each capacitor is same and the voltage drop across each capacitor is different. Let's say V1, V2 and V3 respectively. Then by applying Kirchhoff's voltage law, the algebraic sum of the voltages around any closed loop is equal to 0. We can rewrite this equation as Vs equal to V1 plus V2 plus V3. Since V equal to Q by C, substituting Q by C for each capacitor, this equation will give us Q by C equals to Q by C1 plus Q by C2 plus Q by C3. Here Q is common. So Q by C equals to Q multiplied with 1 by C1 plus 1 by C2 plus 1 by C3. Dividing both sides by Q, we get the value of 1 by C equals to 1 by C1 plus 1 by C2 plus 1 by C3. Therefore, combined capacitance is given by the reciprocal formula 1 by C equals to 1 by C1 plus 1 by C2 plus 1 by C3. If two capacitors 6 microfarad and 3 microfarads are connected in series, then the total capacitance equals to 1 by 6 microfarad plus 1 by 3 microfarad, that equals to 2 microfarads. In series combination of capacitors, the total capacitance is always less than the value of smallest capacitance in the network. Here total capacitance 2 microfarad is less than smallest capacitance of 3 microfarad. The total charge stored across the series capacitors is found by using the formula charge equals to capacitance multiplied with voltage. 2 microfarad multiplied with 18 volts, that gives 36 microcoulombs of charge stored by this series network. The individual charge holds by each capacitor is equal to the total charge. Here the smallest capacitance is the limiting factor. We can find the voltage of each capacitor using the formula voltage equals to charge divided by the capacitance. So in this circuit, the 6 microfarad capacitor will drop 6 volts and the 3 microfarad capacitor will drop 12 volts. The combined voltage is equal to the applied voltage, which is 18 volts. Basically, capacitors are connected in series to provide a higher voltage breakdown rating. For example, if three 200 volt capacitors are connected in series, the combined voltage rating becomes 600 volts, even though overall capacitance is reduced. If we connect a capacitor in series with a lamp and battery, when we close the switch, the lamp will glow and the capacitor starts charging. Once the capacitor fully charged, the lamp will be off. Remember, the electrons cannot flow through a capacitor because of the insulating material inside it. If we remove the battery, then there is no path for the capacitor to discharge. It doesn't matter if we connect or disconnect the battery. The lamp will not turn on. However, if we connect these two lines, we have provided a path for the capacitor to discharge. So the electrons will flow through the lamp and illuminates it. The lamp will be switched off after the capacitor is completely discharged. Now we will discuss about parallel combination of capacitors. By connecting capacitors in parallel, we are essentially combining them to form a larger capacitor. Then the total capacitance value of the parallel capacitor is equivalent to adding their plate areas. Here the insulation thickness remains same, only storage plate area increases. Capacitance is directly proportional to the area of its plates. Larger plates provides greater capacity to store electrical charge. Hence the combined capacitance equal to the sum of the individual capacitances. If we connect a capacitor in parallel with a lamp and battery, when we switch on this circuit, the lamp illuminates and the capacitor gets charged up. The lamp remains on after the capacitor is fully charged. If we switch off this circuit, the lamp will remain on as long as there is charge in the capacitor, because the capacitor is discharging and powering the lamp. If we connect two capacitors in the circuit, we can power the lamp for longer, because the amount of charge stored in the two capacitors are higher. Here we have connected three capacitors C1, C2 and C3 in parallel combination, and 10 volts voltage is applied across them. All the three capacitors are connected between two common lines, let's say X and Y. And these two lines X and Y are directly connected to voltage source of 10 volts. Hence voltage drop across each capacitor will also equal to the applied voltage of 10 volts. The charge stored in a capacitor Q equals to capacitance multiplied with voltage. Since voltage across each capacitor is same as supply voltage, the charge stored across each capacitor is directly proportional to its capacitance. Let's say them Q1, Q2 and Q3. The total charge Qt equals to the sum of the individual stored charges on each capacitor, Q1 plus Q2 plus Q3. Since Q equals to C into V, we can substitute Q1 as C1 into V, Q2 as C2 into V, Q3 as C3 into V. Here V is common. So C into V equals to V multiplied with C1 plus C2 plus C3. Dividing both sides by V, we get the value of C equals to C1 plus C2 plus C3. Combined capacitance equals to sum of the individual capacitances. If C1 equals to 10 microfarads, C2 equals to 20 microfarads and C3 equals to 30 microfarads, then the total capacitance of this parallel combination is 60 microfarads. The total charge stored by this parallel combination of capacitors Q equals to C into V, that equals to 0.006 coulombs. Now let's solve one example based on series and parallel combination of capacitors. Here in this circuit, we will try to find out the total capacitance. All capacitors are same value of 2 microfarads. If we observe this circuit closely, these two capacitors are connected in parallel. So combined capacitance equals to 4 microfarads. So these two capacitors can be replaced with one 4 microfarad capacitor. Now the circuit looks like this. Here these two capacitors are connected in series. So the combined capacitance equals to 4 by 3 microfarads. Now we can redraw this circuit with one equivalent 4 by 3 microfarad capacitor. These two capacitors are connected in parallel combination. So we can replace them with one 10 by 3 microfarad capacitor. Now this circuit looks like this. Here also these two capacitors are connected in series. So combined capacitance equal to 5 by 4 microfarads. Here we can redraw the circuit like this. That's just two parallel combination of capacitors. So the total capacitance of this circuit equals to 13 by 4 microfarads. This is how we can find out total capacitance value of series and parallel combination capacitors network. That's all about series and parallel combination of capacitor circuits. If you have learned from this video, please do mention them in the comment section. In next video, we will discuss about inductors. Thanks for watching. If you like this video, please click like button. Help others to learn by sharing this video. Please subscribe and turn on notifications for more such videos. Have a nice day.